Hi everybody, and welcome to video number 5 of our Unit 2 bonding video series, where we take a look at why ionic bonds only happen between metal and nonmetal atoms, while covalent bonds occur between two or more nonmetals only. To do this, of course, we have to recap some things from some of our previous videos. In video 2 of the series, we introduced ionic bonds. We said that they occur when electrons are transferred from a metal to a nonmetal atom. You probably remember lithium and fluorine, both unhappy atoms because they need noble gas configurations. They don't have them. They're chemically unstable. To fix this, lithium transfers. It actually moves its valence electron to the fluorine. Now, lithium has a noble gas configuration, so does the fluorine. Even more importantly, they're now charged, oppositely charged, so they will be attracted to one another. Covalent bonding happens very differently. In videos 3 and 4, you saw that covalent bonds occur when electrons are shared between nonmetal atoms. We started with two fluorine atoms, neither of which has a noble gas configuration to get it. They move closer together until they can share a pair of electrons. The benefit is, now they both do have noble gas configurations. We left out one really important piece from these videos, however, and that is the why. Why do metals lose their electrons, and why do nonmetals not do that? Why do they keep them? It's a really important question to answer to really understand chemical bonds. So let's start with the ionic bonding and ask the simple question, why are electrons transferred from metals to nonmetals? The answer has to do with actually the periodic table and the general positioning of these two groups, the metals down here on the bottom left and the nonmetals up here on the top right. If you think back to Unit 1, where we learned about the periodic table, all the atoms over here on this side of the table have similar characteristics, two of which matter here. These atoms have low ionization energies and low electron affinities. These just happen to be all the metals. What this means is that metals are very willing to lose electrons. So when we talk about lithium, that is a metal over here on the left side of the periodic table. It's very willing to give its electron to fluorine. Fluorine, on the other hand, is a nonmetal. Nonmetals have very high ionization energies and high electron affinities. Therefore, they're the ones that are more likely to gain electrons. So when you put a lithium atom next to a fluorine atom, that's just what they're going to do in order to satisfy the octet rule. That same idea answers the question, why are electrons shared between nonmetals? If you get these two fluorine atoms near each other, they're both nonmetals. Neither is willing to lose an electron. So all they can do is move close enough to share two electron pairs between them, forming a covalent bond. This actually brings up one other really important difference between ionic and covalent compounds, and that difference has to do with what these two different substances look like, or how they exist in nature or in real life, however you want to say that. Ionic compounds do not exist as individual molecules. Let me show you what I mean by this with lithium fluoride, the same substance we've been talking about for the past 4 or 5 videos. You already know that lithium fluoride exists as one positive lithium attached to one negative fluoride ion. But what you may not know is that this pair does not exist alone, individually. That next to it, there's probably a whole separate lithium fluoride where a second negative fluorine attaches to this positive lithium, and there's another positive lithium here, and this can expand onwards and outwards, technically indefinitely, or at least until you get a pretty big chunk of Li and F ions. What we call this is a crystal structure of repeating three-dimensional units. What really matters here is that when you write that formula for lithium fluoride, LiF, it's only showing the ratio of ions in the crystal structure. So LiF would indicate that there's one lithium cation for every one fluoride ion, but no individual LiF molecule. If we compare this to covalent compounds, these things do exist as individual molecules. F2 probably would look more like this in real life. F2 is separate from this F2 molecule, which is separate from this F2 and this one, and this would carry on for however many F2 molecules there are. Understanding this difference is a really important part about understanding ionic compounds versus covalent ones, and it's going to help you to explain tons of different things later on. Thank you very much for watching. Please enjoy the recap to follow.